Friends, welcome to this very first session of Learning is Fun with Dr. Pawan, powered by Micah. Today, what we're going to cover is a session on real numbers. What are real numbers? Euclid's division lemma and applications of Euclid's division lemma. Okay. Now, for the students who study in India and are in class 10, it is the first chapter of the ncert textbook, and we'll be covering what real numbers are, the concepts, and as I said, the Euclid's division lemma. So to begin with, let us start with how it all started. So it all started with what we call as natural numbers. So natural numbers in my view, the name came because they are all existing in nature, which means that anything that we have in nature, okay, it could be the sun, the planets, the trees, the leaves, everything is counted in terms of natural numbers. So for that matter, our fingers, we have 5 fingers each hand. We don't have 6.3 fingers, 5.2 fingers. Okay, so natural numbers are the set of all numbers which begin from 1, 2, 3 and go on to infinity. Okay, infinity can also be denoted by this symbol. In general, the set of natural numbers are denoted by the alphabet N, capital alphabet N. Then, when 0 got discovered, of course, Aryabhatta has been given the credit of discovering 0, but when 0 got discovered, men got thinking, oh, why not include this 0 as well in the set of numbers? And that's how we came to whole numbers. Whole numbers. So if you see here, whole numbers, which means numbers begin from 0, 1, 2, 3 and they go on to infinity. And by the way, whole numbers are denoted by the capital alphabet W. Okay, in a way we can also say that W equals to 0 plus N, which is natural numbers. Okay, so now we get next set of numbers, which are your integers. So integers are set of all those numbers where you have 0, positive numbers and negative numbers. Sometimes we also call positive integers negative integers because we have 0 in the center, the right side is your positive side, so here 0, 1, 2, 3, 4. Here you have -1, -2, -3 and so on. The arrows denote that these will go on, and this is a simple number line representation of the integers. Integers, by the way, are denoted by Z, and integers, as we can see, they cover whole numbers here, 0 and positive numbers plus the negative numbers here on the left hand side. In the last session in cbse class 9, you guys studied about rational numbers. Rational numbers are the set of all those numbers which can be represented in the form P by Q. Now that got me thinking as well. So what is P and what is Q? English, maths, are we mixing it? Anyway, so here rational numbers are the set of all those numbers which can be represented by the form P by Q. Now we'll count what P and Q mean. where q not equal to 0 and p and q are both co-prime. Here, p and q are integers and q cannot be equal to 0. So what we are saying in a very simplistic manner is that your fractions typically are your rational numbers, where p and q both have to be co-prime. Now what do we mean by co-prime? Co-prime means that the numbers are prime to each other, which means they don't have a common factor between them. Let us take an example. 4 is a composite number. 9 is also a composite number. But when we talk about 4 and 9, both are co-prime because 4 and 9 have no factor in common. Okay? So 4 by 9 is a rational number, where this guy at the top of the line is called numerator and this guy here is called the denominator. Okay? So, rational numbers in a way is a superset again of all these numbers. It is a whole natural number, whole number, integers. So, sometimes students come to me and say, sir, rational numbers are just p by q, which means they are just fractions, sir. How can integers be rational numbers because integers are not fractions? So, my dear friends, rational numbers are also integers, whole numbers, and natural numbers. Why? Because if you take the number 4 for example, it always has a denominator 1, so you still see this p by q form holds true. If you have 5, this 5 still has 1 in the denominator, so p by q form still holds true. So which means that all these numbers are also rational numbers. There's one more way of looking at it. Rational numbers are also all those numbers which are having terminating decimals. Okay? If they are non-terminating, then they are recurring in nature. What do I mean by this? So for example, let us say an example of 1 by 5. Okay, so 1 by 5 can be simplified as 0.2, which means if I divide 1 by 5, I'll get 0.2 and this guy here gets terminated, which means I don't have any further numbers. Okay, so this is a terminating decimal, an example of rational number. But suppose, say, we don't have numbers which terminate when divided. Let us take an example of 1 by 3. Okay, so 1 by 3 when solved is 0.333 ... and you can write it to the end of the page as much as you want, but this 3 will go on. Okay, so if you see, this decimal is recurring in nature. So we're discussing about rational numbers. Now rational numbers, as I was saying, is set of odd numbers which can be denoted in the form of p by q. There's another way of looking at rational numbers. If we have to identify rational numbers, all the terminating decimals are rational numbers, which means after the decimal there will be no further repetition of numbers. Okay. Also, if they are not terminating, which means 1 by 3 for example, if we divide 1 by 3, this 0.333, it's non-terminating in nature, but it is recurring in nature, which means 3 is repeating itself. So this also is a rational number. Okay. Now, we could also encounter numbers which are non-terminating and non-recurring. All those set of numbers are called irrational numbers. Okay, so you have irrational numbers. So So one of my students tell me, sir, irrational numbers are set of all those numbers which cannot think rationally. Okay, but you can say that irrational numbers are set of all those numbers where the numbers are non-terminating and non-recurring as well, which means if you have a number 0.10101000100000 this is non-terminating as well as non-recurring. You could have another example 2.31311131111111. Okay, so as we see, there is no pattern that we are forming here. Okay, whereas in the case of rational numbers, we have a pattern in place. Okay, so here this 0.3 is also written as 0.3 bar. This bar is called vinculum. Okay, and this means repetition, continuity. Okay, you can also place a dot. Okay, so 0.3 bar. This bar denotes that 3 will go on and on up to infinity. Now we come to our main topic, which is our real numbers. So real numbers is the superset of all these numbers. Okay, so all these numbers, as we see, natural, whole, integers, rational, irrational. This is like the universal set of numbers. Okay, so it's like your big Thanos having powers of all the infinity stones and other stones. Okay, so this is real numbers, a superset for you. So this comprises of all the numbers. So this is a universal set. Okay, as the rational numbers denoted by Q plus irrational numbers denoted by I. Okay, all the numbers belong to real numbers except root of negative numbers. So if you have root of -5, this is not a real number. So where does it go? It belongs to another set of numbers which you will study in your higher standards. For CBSE, this will be in 11th if you're taking science as a stream. This is known as complex numbers. So simplistically, the root of negative numbers are your complex numbers. So now we move to our next topic for the day, which is Euclid's division lemma. Now this again is a very simple concept, extremely simple. Don't go by its name, Euclid and division and lemma. It's a very simple concept. So before that, let us quickly revise. You have natural numbers beginning from 1, 2, 3 and on. Whole numbers starting with 0 to infinity. Integers, negative, 0, positive numbers. Rational numbers, numbers of the form p by q, q not equal to 0, p, q are coprime. I explained what coprime means. Irrational numbers which are non-terminating, non-recurring in nature like this. And then real numbers, which is a set of all these numbers, it's like a universal set barring root of negative numbers. Okay, so we now move to another topic, which is Euclid's division lemma. So what does Euclid's division lemma tell us? Euclid's division lemma Euclid's division lemma is a very simple concept where it says that any number can be represented by the form PQ plus R. Okay, now what is this? So let us take a very simple example. Say you have number 5, okay, and you are dividing this number by 2. Okay, so obviously you know you're smart enough, 2 2s are 4 and you have 1 as the remainder. Okay, so now here this guy is known as dividend. This guy here is known as divisor. My friend here 2 is your quotient, and this aloof guy here is your remainder. Okay, so if you look at it, your 5 is 2 into 2 plus 1, 2 into 2 plus 1, which is 5 equals to PQ plus R, where R is your remainder, Q is your quotient, and P is your divisor. 5 of course is your dividend. Okay, so simplistically this is your Euclid's division lemma, and we use Euclid's division lemma to find HCF of numbers. Okay, let us take an example as to how we can find HCF of two numbers using Euclid's division lemma. Okay, I'll rub this. You're smart enough, you grasped. Let us say you have to find HCF of two numbers, and let us say the numbers are 120 and 24. Okay, and you have to find HCF of these numbers. Okay, what is HCF? It's highest common factor. Sometimes this guy is also called GCF, which is greatest common factor. Okay, means the same. Ultimately means what is the maximum that is common between two numbers. Okay, so now I have to find HCF of 120 and 24 using Euclid's division lemma. So how do we start? So I told you just before this that Euclid told us that any number can be represented in the form PQ plus R. So we will be doing the same. Okay, so 120, if I have to represent it as a form of this, I'll divide it by 120. Okay, so you can divide 24 into 5 plus 0. Okay, oh my god, we got a 0 here. Okay, so when you have remainder as 0, okay, the divisor here becomes the HCF. Now this was very simple. Okay, let us take another example. If you have to find, say, HCF of 240 and 36. Okay, let us find the HCF of 240 and 36. So we have to represent 240 in terms of 36. Okay, so 240 equal to, let us divide 36 is 240. Have to do a table here. It's 5 are 6 here. 6 6 are 36, 3 6 is 18, 2 1 6. Okay, so 2 1 6, and if we have 36 into 7, it will go beyond 240. So this is 36 times 6. Okay, plus your remainder will be 24. Okay, so what we have done is we have represented 240 as 36 times 6 plus 24. Okay, now next, what do I have to do is I have to represent this divisor as a form of this remainder. So 36 is equal to 24 into 1 plus 12. Okay, 36, this divisor I have to represent in the form of this remainder. So 36 equal to 24 into 1 plus 12. Okay, now again repeating this process. This is the divisor, this is the remainder. I have to represent 24 in the form of 12, so 22 plus 0. We have reached 0. So as I had said, when we reach 0, the divisor is our answer or our HCF. One other way of looking at it is the remainder before the 0. The remainder before 0 is also our answer. So our HCF of 240 and 36 is 12. So HCF 240, 36 using Euclid's division lemma is 12. Okay, very simple. I hope you have understood. Please try similar kind of sums. If you have doubt, please reach out to me. Till then, keep smiling. Learning is fun. See ya. Bye bye. Take care.